All right. So our first reaction here puts on that SO3H, a sulfonic acid group. It's my first reaction. You can write SO3H, but your homework's going to make you draw out the full Lewis structure. So just to be good, draw out that full Lewis structure here. All right. And then I'm going to do a follow-up reaction, what we call a Friedel-Crafts alkylation reaction here, adding these two carbons onto the ring. But now that I already have a substituent on there, the question is, where does it go? Right? I would get a different product depending on whether it was added to the ortho, meta, or para position relative to my sulfonic acid group. So what I got to do is look at what's already on the ring, this SO3H, and I got to ask myself, is this an ortho-para or a meta-director? So what do we have for the SO3H? This is a meta-director. So those incoming substituents are going to be directed to the meta position. All right, and again, it's two carbon alkylation here. So boom. All right, if I do it in the other order here, let me make a little bit more room. Now my alkyl group, my ethyl group is going to be added first. So now I got to look at that alkyl group and ask myself, is this an ortho-para or a meta-director? This one's ortho-para. These are only ortho-para directors that don't have a lone pair directly next to the ring. We just got to know. So that means I'm going to have one product, my ortho product, and I'm also going to have my opposite side of the ring, my para product. All right, so again, all that to say that depending on the order in which you do these reactions, you can get a different product, right? In both cases, I have an alkyl group and a sulfonic acid group on the ring, but the question is, where are they relative to one another? The first group that you put on there is going to direct the incoming substituent to a particular location. All right, so now we're going to complicate all of this here today. Okay, first thing what we're going to do is we're going to introduce what are called blocking groups. Okay, we did in a previous example that alkyl group, and we got a mixture of our ortho-para products. Let me just copy a benzene ring. Okay, but we also talked about how if we used a very large group, so let's just use a very bulky alkyl group here. If we were to perform a subsequent electrophilic aromatic substitution reaction, so we'll do a bromination. Our mixture of ortho and para products would be really skewed towards one of these two products. And that would be our major product, would be that para product. Because of what we call steric hindrance. Okay, but what if I really want that ortho product there? I really want to direct that incoming substituent to that very crowded ortho position, right? We can make this our major product. using what's called a blocking group. Okay, so a blocking group is a group that can be added using that normal electrophilic aromatic substitution reactions. But importantly, for it to be a blocking group, it also has to be able to be removed at a later step. Our blocking group is actually one that we've already seen before. It's that sulfonic acid group. All right, so if I take this and I first add that fuming sulfuric acid, my major product of this reaction, because I have that big bulky group, we'll have that SO3H group in that ortho position. I'm sorry, in that para position. So now, if I do my bromination reaction, okay, my alkyl group is orthopara, but that para position is currently blocked. So the only positions open are that ortho position. And that sulfonic acid group is what? Orthopara or meta-directing? Meta. And if I look at the positions that are meta to that sulfonic acid group, they're those same two carbons. So even though those carbons are sterically hindered, both of my groups are going to direct there, and there's no other choice. So when I add my bromine to my ring, it's going to be added to those two, to one of those two carbons. But again, it's not really a blocking group unless you have the ability to remove it. Turns out that this is going to be a new reaction here, but it's very easy to get rid of that sulfonic acid group. All you have to do is put it with a dilute solution of sulfuric acid. Okay, so the first thing we did with that sulfuric acid was we added a blocking group. That had the effect of occupying that preferred para position, so that when we did our subsequent reaction, the only choice of where to direct that incoming electrophile was to that, from our alkyl group's perspective, that ortho position. Then we did our electrophilic aromatic substitution reaction, added that bromine, and then we removed that blocking group. So that now our major product is that previously sterically hindered bromine in the ortho position. Right? So one strategy that we can use to get a particular product is using these blocking groups here. Okay, The next set of reactions are ones that we actually already covered, but we want to make sure to look at them in a particular light here. This is a way that we can convert orthopara to metadirectors or vice versa. All right, so if we started out with, for example, toluene, what do we know about that methyl group there? Orthopara or metadirecting? Orthopara. In fact, we can be even more specific. This is what we would call a weak orthopara director. All right, but if we rewind back to last chapter, we learned that we can take these benzylic carbons and we can perform an oxidation reaction. And we can oxidize that carbon all the way to a carboxylic acid, a fully oxidized carbon here, creating benzoic acid. Now, again, we've already covered these reactions, but we want to put them in this particular category here because, again, toluene is an orthopara director, but what is benzoic acid? That's a metadirector with that carbonyl group directly next to the ring here. This is what we would call a moderate metadirector. So we've converted what was an orthopara director into a metadirector. Okay, so this is important to keep in mind in terms of our synthesis strategies. We have the ability to convert something that used to be orthopara into something that is now a metadirector. All right, likewise, we can take that same reactant here. We can do our other benzylic reaction here. We're going to use a huge excess of NBS. NBS will brominate that benzylic position, and if we use a ton of it, it's just going to occupy all possible sites with a bromine. And that fully brominated carbon there would be a strong metadirector. So again, converting something that was an orthopara director into a metadirector using one of those reactions at the benzylic position. All right, so we're going to introduce two more here. We've already talked about them, but nonetheless. But before we do that, let's practice this real quick. Before we got too many reactions to keep track of here, why is this important? All right, we're going to take benzene, all right, and you're going to create, or rather propose, a synthesis pathway to create from benzene para-bromobenzoic acid. All right, you can use any reagent you want to do it here. Okay, but you need to convert that benzene to parabromobenzoic acid. All right, everybody take a minute and see if you can't come up with a pathway to do it. Okay, there's actually two different ways to do it, but I'm going to try to make a point here. So the first thing I'm going to do is add that extra carbon to the ring using that electrophilic aromatic substitution reaction, the Friedel-Crafts alkylation reaction. Okay, now from here, I got two other steps that I need to do. I need to add a bromine to the ring, and I need to turn that alkyl group into a carboxylic acid. Okay, so let's say that my instinct is to first do our oxidation reaction. Well, now, if I did my bromination reaction, where would that incoming bromine be directed? Into the meta position. And is that what I want for my final product here? No. So importantly, I'm not going to go this path. I'm going to first convert toluene, brominate it. I'll get a mixture of both the ortho and the para, but in this case we're only interested in the para product. I'd have to do like some chromatography or some other sort of separation technique at the end to get rid of my extra one, but that's okay. We got plenty of lab techniques to separate out compounds. And now I can oxidize in order to get my benzoic acid derivative here. All right, so the order in which we perform these conversions are really important. If we first converted to benzoic acid, we would not get the product that we wanted because benzoic acid is a meta-director, right? But if we wait until the end to convert, then we'll have our product. Now, you could have avoided this problem altogether by just starting with bromine first. That would have also worked. All right, but nonetheless, just sort of trying to highlight what these sort of reactions are doing for us here and how they're going to complicate things / expand our possibilities of what we can make. All right, so let's look at a few more of these reactions here. Another one that we learned how to do we can take our Friedel-Crafts acylation product Is that an orthopara or a metadirector? That one is a metadirector, what would be considered a moderate metadirector. Okay, and we learned how to chop off that oxygen, fully reduce that carbon using zinc, hydrochloric acid, and heat. That would convert to just ethylbenzene. And ethylbenzene is what? Orthopara or metadirecting? Orthopara. So now we have a weak orthopara director. All right, and the last one that we're going to add to this list of these 4 important conversion reactions is if we start out with nitrobenzene. Nitrobenzene is a strong metadirector. All right, we can convert this to just aniline. Using another sort of zinc-based reduction technique. This one you break up into 2 steps. I trust them. To be honest, I don't know. I mean, I'm imagining that sodium hydroxide is an important role here. I don't know exactly what it does, I'm not gonna lie. But aniline is not a metadirector, but a strong orthopara director. All right, so these 4 reactions we've covered up until this point, but are really important to kind of keep in mind here in the context of, chaining all these electrophilic aromatic substitution reactions with one another, because they allow us to convert orthopara directors to metadirectors or vice versa, depending on what reaction we're starting with here. Okay. Let's try to do one more example here. We want to convert benzene into this guy we don't know how to name. We're aniline with a sulfonic acid group in the para position. This is a little bit better example than the previous one, because this one there's only one way to do it to get your desired product. so first of all, sort of my strategy for how I would go about this here is I'm going to look at these rings and I'm going to try to think of everything I can do that would put on these two groups here. Right? So adding that sulfonic acid group, how do we do that? That's our fuming H2SO4. And what about this amine group here? All right? We don't know how to do just one reaction that sticks an NH2 onto that ring, right? Instead, what we would have to do is first make a nitro group on there. Right? That would be one reaction that we would use. And then we would have to convert that nitro group into aniline using that zinc, HCl, and NaOH. So we have these three reactions here that would put these things on the ring. And now the question is, what order do we do these reactions in? All right? So some trial and error is going to help us out. All right, let's say that first I want to use that fuming sulfuric acid. All right, and then I'll do my nitration reaction. Well, if I do it in this order here, where is that incoming nitro group going to go? To the meta position, because that sulfonic acid group is a meta director. All right, cool. Is that going to help me get to my product? No. These are spaced out incorrectly, right? So there's no way to then make that jump over here. So this route isn't going to work. All right, so then let's try our other reaction first. We'll do the nitration. All right, so if I do my nitration first and then do my fuming H2SO4, where's that sulfonic acid group going to go? Again, to the meta position. So again, I don't want to do that. That's going to put it in the wrong place on the ring. So instead, what do I have to do next? I don't know that we have a name. You're going to reduce that nitro group using that zinc. Okay, so this would create aniline, and aniline is what type of director? Orthopara. So now we have created our orthopara director so that when we do our final sulfonation reaction. Yes, that is what it is. Should have sounded more confident, but yes. Attach that sulfonic acid group. Now it's going to go, we'll get a mixture of both, but importantly, we'll get our desired product where that SO3H is in our para position. Okay? So we did a little trial and error. I mean, it's great if you can look at those three reactions and see the order in which they're supposed to do, you know, just kind of logically work it out. But again, just trial and error, you can kind of just start mixing and matching until you get to your desired product. Sometimes there may be more than one way to get to that desired product, as we saw with the previous example. Okay? In this case, there would only be one way to organize those three reactions to get your desired product here. All right? So you can see how by introducing these ortho to para to meta conversions here, we can kind of complicate things, or, from a less cynical perspective, we can open up more possibilities for what we can synthesize in the lab. All right, so one more type of reaction to throw into this chapter. These are now what are called not electrophilic, but nucleophilic substitution reactions. Nucleophilic aromatic substitution reactions. All right, so this is where we're going to take our benzene derivative and react it with a nucleophile, and it's going to do the same kind of thing where it's going to substitute out onto our ring. This is a way more limited category of reactions here. You can't just start with any old benzene derivative to do it. There's actually some pretty stringent criteria here for the type of substrates that we can use in these reactions. All right, number one, benzene is going to be playing the role of the electrophile in these reactions, right? It's going to be attacked by a nucleophile. And benzene's this very electron-rich ring structure. So the only way that you can get benzene to play the role of an electrophile is if there is a strong electron withdrawing group on that ring. All right, so step one, in order to undergo nucleophilic aromatic substitution, you need to have benzene with a strong electron withdrawing group. And those electron withdrawing groups are what? Ortho-para or meta-directing? Meta. All right, so we got to have a strong meta-director on that ring, right? Again, it's got to withdraw a bunch of electron density so that benzene can actually play the role of an electrophile. All right, so if we go back to our cheat sheet of these benzene derivatives, all right, we had these three strong meta-directors, strong electron withdrawing groups here. All right, so just note our nitro group. This is our carbon with 3 halogens on there. Again, we know how to create this from toluene by using an excess of NBS. And then this one that we don't know how to make, but nonetheless is a strong meta-directing group. So you have to start out with a benzene derivative that has one of these 3 strong electron withdrawing groups on it. So again, we're already limiting ourselves to a kind of small subset of possible molecules. All right, and then not only does it have to have that strong electron withdrawing group, it also has to have a good leaving group, aka one of our halogens. That is either ortho or para to that electron withdrawing group. All right, so again, 2 pretty stringent criteria here of what we can start out with for our nucleophilic aromatic substitution reactions. Number 1, we got to have a strong electron withdrawing group, something like a nitro group on there. And number 2, we have to have a good leaving group, one of our halogens that is either ortho or para to that electron withdrawing group. All right, if we meet those 2 criteria, then we can react this molecule with a nucleophile I'm going to use just generic Nu for my nucleophile right now. And what we're going to see is our nucleophile is going to be substituted onto our ring, taking the place of that good leaving group, taking the place of that halogen. All right, so if we have a benzene derivative that meets these two criteria, we can react it with a nucleophile and substitute that nucleophile onto our ring. All right, let's take a look at some of the nucleophiles that we can use for these reactions. All right, so importantly, are nucleophiles electron-rich or electron-poor? They are electron-rich, so these are going to be all of our electron-rich species here. All right, so one giveaway for an electron-rich species would be what charge, positive or negative? Negative, right? So your good nucleophiles, not all of them, but 99.9% of them have a net negative charge associated with them, all right? And we tend to see the same few elements. So for example, oxygen with its 3 lone pairs will have a net negative charge, all right? So oxygen as a nucleophile. This could be a deprotonated alcohol, what we would call an alkoxide ion. All right, even more stable than an alkoxide ion would be a carboxylate ion. It's got that oxygen now to help stabilize that net negative charge. All right, or we could have the simplest possible oxygen with a net negative charge, a hydroxide ion. All right, much harder to do, but nonetheless also good nucleophiles would be if you deprotonated a nitrogen. These are much harder to do. Nitrogen holds on to its hydrogens much more strongly, but it is possible. Okay. So again, you could have a deprotonated amine. You could have a deprotonated amide, where that nitrogen is bound to a carbonyl carbon. Or again, the very simplest would be if you take ammonia and deprotonate it. All right, just some pain in the ass terminology here. These functional groups we call amide functional groups. But for no good reason at all, this molecule is also named the amide, or amide. I don't know how they say it, maybe they pronounce it differently, but spelled the exact same. All right, some people say amide, some people say amide. I just pick one and stick with it. Not sure if I'm right or wrong, but that's what I roll with, all right? Okay. And then the other one, which is even harder to do, so you'll see it sort of only in special cases, would be if you had a carbene ion. Carbon really doesn't like to give up its hydrogen, so there's really sort of 2 special cases that you will see. When it's triple bonded to nitrogen, what's called a cyanide ion. Okay. The other thing is, back in the first semester, you would have learned that you could actually deprotonate terminal alkynes as well. So if we have a carbon that's triple bonded, we can remove that hydrogen. And these are also really good nucleophiles. All right, and then the last one that we're going to note here is an element that just because of its size and its electron density is just really good at being a nucleophile. It turns out that it's just a very bad base, which is usually a competing reaction with nucleophiles. So it just makes it really prefer a nucleophilic substitution reaction, and that is sulfur. Sulfur as an element is just a really good nucleophile, so much that even using a neutral thiol would be fine as well. Right? So you can either have it neutral or you can deprotonate it. Either one is a good nucleophile. All right? Every other nucleophile we saw here had a net negative charge. Sulfur is one element that you want to note is just really good at being a nucleophile. Okay, so again, I can have a regular old neutral thiol, or I could deprotonate that thiol, and both of these would work in a nucleophilic aromatic substitution reaction. All right. Cool. So let's just do an example here. We're going to take our candidate for our nucleophilic aromatic substitution reaction, and we're going to react it with one of our nucleophiles. Let's just do hydroxide. All right, everybody take a second and give me the product of this reaction here. So again, that nucleophile is going to displace that leaving group, leaving us with this nitrophenol, paranitrophenol here. Okay, so these nucleophilic aromatic substitution reactions we're going to throw into the mix here. We can start mixing and matching. I could do a subsequent reaction here, like for example, a bromination. Right, I could now do an electrophilic aromatic substitution reaction, and we would have to look at what our substituents are on our ring. Are they ortho, para, or meta-directing, et cetera, et cetera. So this is just going to fit right into our network of discussing our electrophilic aromatic substitution reactions. All right. This is like done with kind of new content for this chapter, but we just piled a lot of crap on top of what we learned last week. So next class, we're going to just sort of go over and review and sort of explore all the different avenues that we can do with all these reactions that we covered here, what we would call our synthesis strategies with all these benzene derivatives. Remember that your first exam is when? Yeah, next week on Monday and Tuesday, all right? So a week from today. So how this is going to work is next class period, we'll kind of close out this chapter 18 material. On Friday, we're going to rewind back and do a bunch of review. On Monday of next week, if you can make it to this lecture, great. We'll just do more review, more practice problems. If you're going to use that time to take your exam, that's perfectly fine as well, all right? On Monday of next week, I won't be taking attendance in here. So if you can come for the review session, great. If not, if you want to use that time to take your exam, go for it, all right? Cool. What's up? All of your homework can be redone, and there are practice assignments that have been created in the Exam 1 module that is just additional problems for you to do. There's a study guide, all that jazz.